In this video, I will characterize the convergence of power series. What do I mean by that? We'll show three exclusive cases. So this is the theorem that I would like to discuss. So suppose we have a sequence of elements in R. Here Cn is a sequence, and we have an A in R, and we look at the power series which is built up from the sequence Cn and powers of x minus A. Well, then this series that I have here on the right hand side is called a power series centered around A. I will show the following, that there are three exclusive cases. There are three cases. The first one is that this power series only converges if x equals A. Well, that it always converges in x equals A is rather clear, right? So for x equal A, x minus A is 0, right? So this infinite sum reduces only to a fixed element, and that's the first element, that would be C0. All the other powers vanish. So clearly we then have convergence of this power series. But the first one is, so here we have point 1, is that the series only converges if x equals A. Secondly, suppose the series converges for all x in R, right? So that this series would be valid, this sum would be convergent for all x's. And the third one, that's the other case, is there is a positive value, a positive number R, such that the series converges for all x's such that the distance to A is not so large, or at least smaller than R. And at the same time, if we take the distance from x to A larger than R, then the series will diverge. Okay, these are the three exclusive cases. I will now show a proof of this theorem. First I will treat some examples. So as an example of the first case, look at the series built upon the series n factorial. So Cn is n factorial. A is 0, so this is clearly a power series centered around 0. Yeah, x minus A is just x. And we sum up over n is equal to 0 to infinity. What can we say about convergence of this power series? Well, we perform the ratio test. Of course, we have convergence for x equal to 0, right? For x equal to 0, we just get the fixed element 0 factorial, which is by convention equal to 1. Okay, but now we perform the ratio test for x unequal to 0. If x is unequal to 0, we perform the ratio test of two consecutive terms from this series, this power series. Yeah, so here we take, as we've done before, a n equal to n factorial times x to the power n. So what we then get is the following ratio, is n plus 1 factorial times x to the power n plus 1 divided by n factorial x to the power n. So we see that we can cancel the x's, right? And also here we can cancel the factorials. So we stick to what is remaining is n plus 1 times the absolute value of x. Yeah, clearly, since x is not equal to 0, this has as a limit infinity for n going to infinity. Yeah, so we only, in this case, in this example, we see only convergence for x equals 0. If x is unequal to 0, we see that the power series diverges. And the second example, consider the one that we've seen before, the sum over n equals 0 to infinity of x to the power n divided by n factorial. Here we see convergence on the full set of real numbers, right? So for any x in R, this series will converge. Well, this is also easily shown by performing a ratio test. I won't do it here, we did it before. So now look at the third example. So we have the first two ones, right? So where only a convergence at x is 0. Here we see one where we have convergence on the complete set R. And now consider x to the power n divided by n, the sum starting in n equal 1 to infinity. Well, this one we also considered using the ratio test, and we concluded that this, by discussing two special points, -1 and 1, that this one is convergent on a left closed interval -1, right open 1. So in this case, we would say that the radius of convergence is 1. Okay, now the proof. So we'll show the three separate cases. So suppose first we start considering a equals 0, so that we have a power series which is centered around 0. Or the conclusion afterwards is it's very easy to generalize to a unequal to 0. So first we're gonna discuss this case. Suppose that we have the first two cases, right? So nowhere outside x is 0 we see convergence, and the second one is always convergence for any x, right? Suppose these first two are not true, so they do not hold. What it means is that there must be a b and d in R, then there must be a b and d in R for which b and d are unequal to 0, for which we have convergence of the power series when we include b, and divergence when we put in d for x, right? So that's the main thing. We should be able to find two of these points. If we cannot, then we're either in situation 1 or we're in situation 2. So now define the set. Consider the set S equals to all x's, the set of all x's for which the power series converges. Well, this set has some properties, right? So first of all, S is not equal to the empty set, right? So since we assume convergence for B, for instance, right? So first conclusion is S is not equal to the empty set. Secondly, we also have that this set is bounded. Well, why is this set bounded? Well, we know that we have divergence for D, and in the previous theorem, I've also shown once you have divergence for some D, then the series will also diverge for any x which has an absolute value larger than this D. Yeah, so this set is bounded. So all the elements x that for which the series is converging, for these x's, we should have that the absolute value is smaller equal than d, than the absolute value of d. Okay, so now we have a non-empty set which is bounded, and this is a set in R, which means that we can speak of the supremum of S. Yeah, what is the supremum of S? The set S is bounded, but it also, since it's non-empty, it has a least upper bound. The least upper bound is called a supremum of S and denoted by sub S. Well, let's define this to be the number R, right? So we're seeking this number R such that if x in absolute value is larger than this R, then we see divergence, and if x in absolute value is smaller than this R, we see convergence. Okay, first we'll look at the case where the absolute value is larger than R. What does it mean? Well, R is an upper bound for the set S, which means that x cannot belong to S. So if x does not belong to S, then we have that the power series for this x is diverging, right? Okay, that's one part. And if x in absolute value is smaller than r, then what we have is, well, r is the least upper bound, so x is not, the absolute value is not an upper bound for S. So we should have a y in S with y is a larger than the absolute value of x, right? Okay, but y belongs to S, so it means that the power series with y is converging. Okay, now again, we use this kind of domination. Once we have convergence for a y, then we also have convergence for all x's which are in absolute value less than y. So we also have convergence for x. So we have the two cases. So if x in absolute value is larger than r, then we see a divergence. And if x in absolute value is smaller than r, then we see convergence. Okay, this completes the case for a equals 0. Okay, now we consider the general case where we have an a unequals 0 and a power series centered around a. What we do is the very easy trick. We make a change of variables, right? So we make a change of variables. We just write u is x minus a. And then we can write the power series in x minus a as a power series in u, right? Okay, so now we're going to apply the former reasoning to the power series in u, right? So in particular, we see that um, in 3 we had the following, that we see convergence for u smaller than some r and divergence for u in absolute value larger than r. But now return back of the true meaning of u is equal to x minus a. So we see convergence for absolute value of x minus a smaller than r and divergence for x minus a in absolute value larger than r. You see, by this simple change of variable and applying that the fact that now we have u as a power series centered around 0, then we get also the more general statement. And this completes the proof.